Welcome to our classroom. Welcome to the classroom. Welcome to the classroom. The segments where I bring the classroom out into the field. Welcome to the classroom. Today we're talking about landslides. I've created a mountain here. We've got a nice hiking trail. The LEGO geologists are examining the trail. We've got a dried up river at the moment at the bottom, and the problem with water is it's going to erode the toe of the slope here as it flows. So hopefully I can get enough water flow to erode the toe, and the toe at the moment, the base of the slope, is holding this entire mass of sand in place. And we slowly remove some of that, it's going to destabilize the slope and it'll collapse. Trees in the forest can actually be a really good indicator of potential slope problems. In reality, the slope will have many signs before collapse. The trees that sometimes tilt over, so the base of the tree is sliding down the slope and the tree starts to tilt over. That could be an indicator. And if it's been sliding for a really long time, the trees might actually grow with a hook in the base as the base is sliding, but the tree wants to grow vertically. So that we call a drunken forest, and that's a really good sign that you have a slow moving landslide. And other signs might be fractures, especially up near where you might get the release of the material. So here we have fairly uniform sand, but if we had different geological layers and things like that, and rocks might start to show cracking. And so the cracking would show the movement as parts of the slope are starting to slide down and other parts are staying in place. So let's give it a try. Let's see if we can make this slope collapse by flowing water at the base and trying to erode out the base. Our LEGO geologists, they're going to risk their lives to monitor this landslide. Oh, there it goes. So there you can see the big crack forming. We had some smaller landslides happening, and as you can see, it's even time-dependent damage is happening after the fact. So we're propagating cracks throughout the slope, and they might grow with time. If we got another rainstorm, another flooding event, it could, now this is really unstable, and I think we should give it a try and do another rainstorm event. But you can see that we failed here first, another little failure here, and then it propagated. We destabilized the slope, and then the larger section started to move. But our LEGO geologists, they survived the day, and they're getting out of there. All right, here we go. Oh, another little bit fell there. And a little bit over there. There's actually a little bit of movement happening. A bit of sand falling. It's moving ever so slowly. You may not see it on the camera, but there's actually little grains of sand moving. I think if I just tickle the toe here, it'll go. There it is. Now what we have actually is, this is what we call the back scarp. That's the failure surface. What is causing that failure surface? Is it a clay-filled seam in the slope? Or is it a bedding plane? Other features like that that are in the rock or the soil that are the sliding plane. And as you've known from the class, there's many different kinds of failure surfaces, circular, planar, and so on. We have to observe the geological situation of each landslide and understand that scenario and what the potential failure processes might be in the future. And we do that through ground investigations, as well as then desktop studies, and using Google Earth and different things like that. We can observe locations, understand where our high risk zones are, and then put in monitoring. So that's the engineering link. At the end of the day, we need to protect the public that live at the toe of these mountains that have potential failures. Thanks for watching, and I look forward to teaching you more about landslides and monitoring.